So let's see. How do we want to start off by processing a borrow on the protocol? Well, first we need to be able to see how much collateral the user has deposited into the bank across the entire protocol to see how much collateral they have to borrow against. So typically in a lending protocol, you'll have several assets that you're going to have to calculate as collateral. For this protocol, we only have SOL and USDC. So we're only going to check one asset as the deposited value for our total collateral. However, when we deposit, we also have the interest accrued on the deposit amount, just like we talked about in our previous instruction. So we need to take that into consideration too when checking how much collateral a user has. So let's first load in the bank and the user accounts so we have the state to be able to get the information we need for our calculations. So let bank equal, we'll take a mutable reference to the account for bank, and then the same thing for user. And then to get the real-time value of your collateral, we're going to have to load in the price update account. So we'll add that. Let price update. Okay. Now we want to find out what the total collateral is. So we're just going to first define total collateral because we're going to use a match statement and we want to be able to use this outside of the match statement. So this is a U64 type. Okay. Now, the reason we're using a match statement is to see what asset the user needs for collateral here. So we're going to use ctx.accounts, and we're going to get the mint address of the mint account that's being passed through. So to account info key, we're going to delete what Copilot suggested here. Okay, so delete that as well. Okay, so we're matching to the key of the mint address being passed through. Now, so if the key is the user's USDC address, then we're going to calculate the total collateral for USDC. So first we need to load in the price feed. Let's find what the price feed IDs are for both SOL and USDC on Pyth. Okay, so to get the price feed, we're going to have to go to Pyth's website where all their feed IDs are listed. So here you can see the price feed IDs, and we're working with Solana stable. Now first I want SOL. So SOL USD, here's the price feed for it. We're going to copy that. And now let's create a constants file to keep track of this. So in our source, we're going to have a new file for constants. Let's update our mod file to have constants. Okay, and now we'll use anchor. We're going to use the constant attribute. Okay, and now we'll define our first constant, which is the SOL USD feed ID. So pub const SOL USD feed ID. Okay, this is an answer type. And then we're just going to paste in the feed ID that we just copied. Now, as you can see, this is all grayed out. So we're going to update the rest of our mod files to make sure it's recognizing this. So we'll go back to our librs, and we want to mod constants. Okay. And here we go. Sorry, the attribute is actually constant, not with an S. There we go. And there's our first feed ID. So the next feed ID we need is the USDC USD feed ID. So we're going to type in USDC, and here is USDC USD. So we'll copy that feed ID over and bring it into our constants. So pub const USDC USD feed ID. Define the type, and then we'll paste it in. Okay. Now, one last thing we need for using a Pyth oracle is we'll need to define the maximum age. So the maximum age is how long you'll allow from the previous update to make sure that the account is not stale. So here, we're going to allow 100 seconds for the feed to become old. So we'll do pub const maximum age U64 type, and we'll just set this to 100. So the price feed cannot be older than 100 seconds or it will return an error for being stale. Okay, so going back to our borrow file, this is where we're going to start using Pyth to be able to calculate the current USD value of the total collateral of the user on the protocol. So back to our borrow, because the user is passing through the USDC address, it means they're looking to borrow USDC. So we're going to get the Sol feed ID because that means that their collateral is in Sol. So let Sol feed ID equal, and we're going to get feed ID from hex. So this comes from Pyth. So we're going to import this. We'll go back to our price update imports and add in the get feed ID from hex function. Okay. Now, what needs to be passed through as an argument here is going to be the feed ID. So we can just use the constant that we just wrote in our previous file and import it. So we'll use the Sol USD feed ID and make sure we update our import to have Sol USD from our crate. Okay, great. So now that we have the feed ID, we're going to be able to get the actual Sol price from the Pyth oracle. So we can do that with let Sol price equal, and we'll take the price update account, and we're going to call get price no older than, get price no older than, and we're going to first pass through the clock. So we'll do clock get and unwrap that. And then the maximum age is going to be the max age constant that we just defined. And then lastly, we'll pass through the feed ID, which will just take a reference to this variable that we just created. So Sol feed ID. And we forgot to unwrap this, so we'll just unwrap, and there we go. Okay, so now we have the Sol price. So now we need to calculate interest. So we're going to calculate the accrued interest. And since we're going to have to calculate this for both areas of this match statement, we're going to go below and just make a function for it. So we'll do fn calculate accrued interest. And we'll just take in the deposited value. That'll be a U64 type. We'll take in the interest rate. And then the last updated time. Okay. And we'll return a result of type U64. Okay. First, we want to get the current time. So we're going to use the same function we used previously, which is taking the deposited value, multiplying it by e to the power of the interest rate times the elapsed time. So we'll get the current time, and we'll do clock.get Unix timestamp. Now we need the time difference, and that is going to be the current time minus the last updated time. And now we can get the new value. So const new value. And this is the formula for compound interest. So we'll do deposited as an F64 times e to the power of the interest rate as an F32 times the time difference as an F32, cast that as an F64, and then we're going to just be able to return the new value. So we'll go back up to our match statement and pull in this function that we just created to calculate the new value with the accumulated interest. So let's total collateral, and we want the SOL price. So we're going to take, because currently we're keeping this in how many SOL you have. So we're going to multiply how many SOL we have by the SOL price. And the new amount of SOL we have is calculated here by the new value. So we'll do SOL price. And now this returns a price struct, which we can take a look at it. It is the price, the conf, exponent, publish time. All we want here is the actual price. So we'll go back to borrow, and we want SOL price dot price, and we're going to multiply that by the new value. So the new value, let's calculate that. Let new value equal, and we'll do calculate accrued interest. And that's going to take in the user.deposited SOL. Okay. And then we also want the interest rate from the bank. So we'll do bank.interest rate. And lastly, we want the last updated. So we'll do user.last updated. And then we'll unwrap this function. Okay. Now we have the new value. So we can just do the SOL price times the new value. And that is your new total collateral. And we'll cast this as a U64 so they're compatible to multiply. And there we go. Now we're going to do the same thing but opposite for the USD value. So we will do the other half of the match statement. So first we're going to load in the USDC price feed. So let USDC feed ID equal, and we'll get feed ID from hex for the USD feed ID. Okay. Now we're able to get the USDC price by using the price update account. We'll do no older than. We have the clock, we have the max age, and then we have the USDC feed ID. Okay. Now we'll calculate the new value, and we're going to use our helper function we created below, and we'll do calculate accrued interest, the user's deposited USDC. And I think this is where I had a typo. There we go. And then we have the bank interest rate and then the user's last updated time. Okay, and now we can calculate the total collateral here. So total collateral, we'll use the price from the price struct for USDC, cast as a U64 times the new value. Okay, so now we have the total collateral for either asset, depending on which asset that the user wants to borrow. And we're going to check to see if the user is able to borrow it. For this lending protocol, we're using over-collateralized loans, which means that the total collateral has to be equal to or less than the total collateral times the liquidation threshold of the asset. So let's check to make sure that the user is able to borrow the amount that they're requesting without making their account unhealthy. So let's do let borrowable amount equal to, and we'll do total collateral multiplied by the liquidation threshold. and we'll pull that in from the bank. So bank liquidation threshold. Okay. Now we can check to see if the user can borrow the amount they requested or not. So we'll do if the borrowable amount is less than the amount, we're going to return an error code for over borrowable amount. Okay, now we're going to copy this and add it to our custom errors. And we're going to add a message for it. And that is not the message we want. Let's do requested amount exceeds borrowable amount. There we go. And now we want to import from our error codes. So we're going to use create error code. There we go. Let's update our import here, clean that up a bit, and update this. Not sure why that was imported. So far we have checked to see the value of a user's collateral and took into consideration the interest that they've accrued based on depositing the asset into the bank. And now we're checking to see if the requested amount to borrow is borrowable by keeping the account safe by borrowing this amount. And now we're just going to update the state for both the bank and the user. Oh, actually, before we update the state, we actually have to process the transfer. So we're going to make our transfer CPI. First step of the CPI is the accounts. So let transfer CPI accounts. We're going to use transfer checked. We need to import that. And that should come from token interface, which it's not showing. So we'll manually add that transfer. Okay. Transfer checked. There we go. Now we'll scroll back down to our transfer checked struct. And we have from, it's coming from the bank token account because we're borrowing from the bank. It's going into the user's token account. The authority is going to be the bank token account. So let's update this. And the reason is because when we created the bank token account, we specified the authority was itself. And now the mint is going to be the mint account that was passed through. Okay, great. Up next is the CPI program. So this is just going to be the token program. And then now we're going to be signing from the bank token account, which is a PDA. So we have to define the signer seeds for this CPI to process. So let's do, we actually did this. It's very similar to withdrawal because both of these CPIs are coming from the token account. So we can go back to withdrawal and just copy this over because we're using the same PDA from the same token account. Okay, so back to borrow. We'll paste that in. Now that we have our signer seeds, we can make our CPI context. And that is just the CPI program and the transfer CPI accounts with signer, and we're defining our signer seeds. Okay, lastly, we need our decimals, and then we can actually process the transfer. So we'll do token interface, and we'll do transfer checked, CPI account, amount, and decimals. Nice. Now that the transfer happened, now we'll update the state for both the bank and the user. So first we want to be able to take into consideration if the total borrowed is 0. So we'll do some error handling here. So if bank dot total borrowed is equal to 0, we'll set that to amount. Now let's check, it's showing that this isn't part of the bank state. So let's go back to our bank and see if we remembered that. Bank. Okay, so it looks like in our bank, we only saved the total deposits and deposit shares. So let's add in the total borrowed and total borrowed shares because we want to keep track of that as well for the bank. Okay, let's calculate the borrow ratio to be able to then calculate the user shares. So calculating the shares for borrowed is the same logic and the same formula as the deposit shares, just using the borrow ratio instead of deposit ratio. So first we will calculate borrow ratio, and we'll do the amount check divide by the total borrowed in the bank. And then the user shares is going to be the bank's total borrowed shared multiplied by the borrow ratio. As you're following along with this code, if you want to look more into all of these calculations that I'm talking about, all of the calculations are explained and stated in the README of this code in the bootcamp. Next, we're just going to do our match statement again to see if we're updating the state for borrowed USDC or borrowed SOL. So, okay. Looks like Copilot did a good job guessing what we were doing here. So we're doing CTX accounts, the mint to account info. We have the key. If the key is the USDC address, it's going to update the borrowed USDC by the amount and the borrowed USDC shares by the user shares that were calculated. And if not, it's going to update the borrowed SOL by the amount specified and the SOL shares by the user shares we just calculated. Okay, so that's it. We're returning okay. We need to import our E constant to the file. And looks like we have one more error we need to fix. Okay, so sorry, when you have the match statement and you're updating the variable, you don't redeclare your let. So we'll get rid of that, and now that's updated. Okay, so now our borrow looks like it's good to go. We can just clean up a few things in the file. Okay, now we'll go back to our librs and actually use this function. So we'll do pub fn borrow. We're going to use the context with our borrow struct that we defined for all of our accounts, allowing the user to pass through the amount that they want, and then we're using process borrow, and there we go. So far, we've done deposit, withdrawal, and borrow. The last main function for lending is allowing user to repay the amount that they have borrowed. So now let's write the instruction for repay. So we're going to add into our instructions folder a new file for repay. We'll use Anchor here. Okay, we're going to update our mod file. Okay, now let's start, as always, with our struct for our context. So we'll do derive accounts. And this will be our repay struct. We'll start with the signer as the first account that we're going to pass through. And then the mint of the token that the user wants to repay. Okay, and that'll be an interface for mint, so we need to import our mint coming from token interface. Okay. And then up next, we'll need both the bank for the state and then the bank token account. And we'll need to import the bank. Okay. And then this is the bank token account. And we'll import token account coming from token interface. Next, we need the user account. And we'll import user. And then we need the associated token account. And then we'll need to pass through the token program, the system program, and the associated token program. and this is a program. There we go. And the token program is an interface. Just updating our types here. And the system program is a program. Okay, Copilot was a little off with those suggestions. We'll update our imports. Oh, this is a token interface. There we go. Now we'll update our imports. Coming from token interface, and this is just associated token. We'll update this import. Okay. There we go. So there's our struct. Now let's start writing the logic for our repay function. So process repay. We'll do our context from the struct that we just wrote. We'll add in the amount as an argument so the user can specify exactly how much they want to repay. Okay. All right. So let's think about how we're going to do the logic here. So essentially what this is doing is just making a CPI transfer from the user's token account back into the bank token account to repay the amount that they've borrowed. But we'll need to do just a few checks beforehand. These checks are going to be very similar to our withdrawal checks, where we're just checking to make sure that the amount that the user is looking to repay is either equal to or less than the amount that they've borrowed. So they're not making an overpayment to the bank. So we'll first load in the user. And then we're going to find out what their borrowed asset is. But we want to also calculate the interest. We want to take into consideration the interest that the user has had to pay on their borrowed asset. So they'll be able to repay a little bit more than they've originally borrowed to fully repay their loan. So we can do that very similar to how we calculated with withdrawal. So let's just pull this file over and we can reference it. Okay. So we'll do pretty much the same logic here. We're going to define the deposited value, but in this case, it's going to be the borrowed value. And then we're going to find out which asset is being borrowed. So if the key is the user's USDC address, then the borrowed value is going to equal the user's borrowed USDC. Otherwise, let's add our comma. Okay. Otherwise, it will have the borrowed value be the borrowed SOL. Okay. And then now we have this error here. So just to get rid of that, we're going to skip ahead and return our OK at the end. Okay. Now that we have that, we want to load in the time difference between when the user initiated their borrow. So we'll do let's time diff equal, and we'll keep this last updated amount to be from the deposit. So let's have a last updated for borrow as well. So we'll go back to the user, we'll go to state, user, we have last updated, and now we're going to add a last updated borrow. Okay, so the time difference is going to be the user's last updated borrowed, and we're going to subtract by the current time. So clock get Unix timestamp. Now we're going to get the APY on the bank. So let bank equal. Okay. And now we'll do bank's total borrowed. And we're going to add in the interest. So we'll do bank total borrowed. Oh, let's delete Copilot's suggestion here and stick to the same formula we've been using. So total borrowed as an F64, we're going to multiply times E to the power of, and we'll do the interest rate times the time difference. Okay. Close this. And now we'll update the value per share. So let value per share and we'll do the bank.total borrowed divided by the total borrowed shares. And then we're going to update the user value. So let user value equal. So the user value is going to be the borrow value divided by the value per share. Okay, now we need to import our natural log. There we go. Now we can do our check. So we'll do if the amount is greater than the user value, then we have an over repayment. So we're going to return an error from the error code enum, and we'll do over repay dot into. Okay, we want to go back to our error code and update this new custom error. So errors, error code enum, we're going to paste in our over repay and then add a message. And we wrote our if statement with the wrong syntax there. Okay. Now we just need to import our error code. So we'll go back up here. We're going to use create error code. There we go. Now it looks like there's an issue with our accounts. So let's figure out where there's an error. So we have the interface account, token account, user account. Okay, so the user token account should be an interface account. Let's just update that. And there we go. Now our error is gone. So now that we did that check to verify that a user isn't over repaying, we can now process the CPI transfer. So the transfer is going to come from the user's token account and go into the bank account to allow the user to repay their debt. So let's first start out with the CPI accounts. We'll do a transfer checked, and we're going to have to import that. And that should come from the token interface. Okay. Up next is going to be the CPI program, which is just the token program. Then we have the context. And since this is coming from the user's associated token account, it's not a PDA. We don't need the signing seeds to process this. Now, we'll do decimals, and then we can actually process the token transfer. Okay, so now that we've processed the token transfer, we're going to update our state for both the user and the bank. So we'll load in the bank, which have we done that? Yes, we already loaded that in. So we don't need to load that in again. So we'll calculate the borrowed ratio, which is going to be the amount divided by the total borrowed. And then we're going to calculate the user shares, which is going to be the total borrowed shares multiplied by the borrow ratio. And then we're going to write our match statement. And Copilot's able to predict this very well because it's very similar logic to what we did in our previous instruction. So we have our match statement, and then we're updating the borrowed USDC by the amount in the shares or the SOL by the amount in the shares. Now we need to make sure we import our token interface. Okay, now that's imported. And lastly is just updating the bank state. So the bank dot total borrowed is going to decrement by the amount, and the total borrowed shares will decrement by the user shares. Okay, so that looks like everything that we'll need for repay. We're going to now take our process repay function and add it to our librs. So pub repay. Okay, now let's clean up this file. Get rid of this warning from our imports. All right. Now, one last thing, since we did add in our APY after the fact, we want to make sure that when a user is borrowing and depositing, we're updating the user's last update value. So let's go to deposit and check. So we have user last update, and it's the current timestamp. And then when we borrow, at the end of the borrow, we also want to update. We want to do user dot last updated borrow to also have the current Unix timestamp. Okay, now everything is good to go with all of our instructions from the user side of things to interact with the lending protocol. Now we have one more instruction that we want to add, and that's the ability to liquidate. So if you have an account that becomes unhealthy, you want to allow liquidators to be able to come in and liquidate the account. And to do that, we'll need an instruction for the liquidator to be able to run. And that will be the last instruction we'll write for this lending protocol. So now let's create the file for our liquidation instruction. We'll go to instructions, new file, liquidate.rs, and we'll update our mod file. Okay. And then back to liquidate, we're going to use anchor. And now we're going to define our account struct for liquidate. So how a liquidation occurs is a liquidator is able to come to a protocol and repay the debt of an unhealthy account. And in return, they receive the collateral plus a liquidation bonus, which is a percentage of the liquidation amount that they receive to incentivize liquidators to come and liquidate unhealthy accounts on a lending protocol. So let's get started by defining all of the accounts needed. We will use derive accounts. We'll define our struct for liquidate. So the first account that we'll pass through is the signer of the liquidation instruction, which is going to be the liquidator. Now we'll need to have the real-time value of the assets, so we're going to pass through the price update account from Pith. We'll want to update our import. Fix our typo. Now we'll update our import. Now we'll need both mint accounts. We'll need the mint account of the collateral and the mint account of the borrow, because we're going to have two transfers that take place through this instruction, because one is the liquidator repaying the debt, and the other is the liquidator receiving the collateral. So we'll do pub collateral mint. And this will be a mint account. And we'll have borrowed mint. which will also be a Mint account. And then we'll update our import for Mint coming from the token interface. Okay. So now we'll need to pass through the bank for both of these assets. We'll need the collateral bank token account, the borrowed bank, and the borrowed bank token account. So we'll do account, and this will have the collateral mint key as the PDA for the collateral bank. And then we'll do the same for borrowed. And now we'll have to update our import for bank from our state file. Okay. And now we'll need the token accounts for each. So we'll do account, mute, and then the token account has the treasury and the seeds. And then the same for the borrowed. Okay, so we have the treasury and then the mint key for the collateral and the mint key for the borrowed. And now we're going to update our imports for token account. And that is coming from the token interface. Okay, and now we want to pass through the user account for the liquidator. And now we'll need the liquidator's collateral token account and borrowed token account. And then lastly, we need to pass through the token program, associated token program, and system program. And then we need to just update our imports with token interface and associated token. Okay. So those are all the accounts we'll need for the liquidation. Now we can go ahead and process the logic for the liquidation function. So pub fn will do process liquidate. Pass through our context with the liquidate struct. Now we'll load in the collateral bank and the user and the price update accounts because we want to be able to see how much collateral that the user has on the protocol to just verify that their account is unhealthy before processing the liquidation. So let collateral bank, we'll load that in. So now we're going to calculate both the total collateral and the total borrowed. And we're going to do this very similar to how we did in another instruction when we made a match statement and calculated the USD value with Pyth. So let's actually just bring that up to reference so you can see. It's with our borrow function. Okay, so we have our match and we're going to match the accounts with the mint account. But let's do the collateral mint. So if the collateral mint dot to account info dot key if the key is equal to the USDC address, so if the collateral is the USDC, then we'll update. Well, we're going to need the SOL price and the USDC price regardless, so we can calculate that outside of the match statement and then pull it in. So let's go back and add that. So we're going to do first get the SOL price and the USDC price. So we need the SOL feed ID, and we'll do get feed ID from hex. We need to import that from Pyth. And we need to import the SOL USD feed ID from our constants. And now we'll do the USDC feed ID. And that'll be the same. And we'll have to update our import with the USDC USD feed ID. So this isn't being recognized, so let's go back to our constants and make sure that's how we named it. Oh, we had a typo here, so we'll just copy that over. There we go. USD. And now we'll update our borrow with the correct constant name. There we go. Then back to liquidate. Okay, now we'll be able to calculate the price just like we did in our borrow function here. So the SOL price is price update, get price no older than. We're using our max age, which we want to import from our constants. And for some reason, VS Code isn't recognizing these two, but oh, there we go. So we have our SOL price, and now we need our USDC price. Okay. Now we can update our total collateral and total borrowed within our function. So we'll do let new USDC equal and we're going to calculate accrued interest. And we want to import this, but we'll have to go back to our borrow and make this a public function. Okay, and then we'll update our import. Okay, now just to get rid of this error, we're going to add our OK at the end. And there we go. So now we have the new USDC value. So if the collateral mint is equal to the USDC address, then we'll update our collateral to the USDC price times the new USDC. And we're going to initialize total collateral here, and we'll also have to initialize total borrowed. There we go. Okay. And then that means that our new SOL will equal, and we'll do calculate accrued interest for the borrowed SOL. And then we're going to have the interest rate and then the user's last updated. But this is going to be last updated for borrow. Okay. And then we haven't imported the borrow bank yet, so we'll load that in up here. Let borrowed bank, and then take a mutable reference to the borrowed bank. Okay. And then we're just going to update the total borrowed the same way. Okay. And now we'll do the reverse for if the collateral mint is SOL. Okay, we can get rid of that reference. So we have our new SOL, calculate accrued interest, the deposited SOL, collateral bank, the interest rate, and then the user's last updated. That updates the total collateral with the SOL price, and this updates the total borrowed with the USDC price. So now we're able to calculate our health factor. The health factor is going to be your total collateral times your liquidation threshold divided by the total borrowed. If the health factor falls below 1, then the account is unhealthy and can be liquidated. So we're going to first do the calculation to check the health factor. So let's health factor equal, and we'll do total collateral divided by total borrowed. But we're going to update the total collateral to be the total collateral times your liquidation threshold. Okay. Now that we have the health factor, we can verify if the account is unhealthy to be able to be liquidated. So we're going to add a check here. So if the health factor is greater than or equal to 1, then we're going to return an error that you cannot liquidate the account. So we'll do return error. We'll use our error code enum, and we'll do not under collateralized. And now we're going to go back to our error code and update this. And here we have a typo. This should be a health factor. There we go. So error, we'll paste in our not under collateralized error, and we'll do users not under collateralized, so it can't be liquidated. There we go. And now we want to import our error. Okay. Let's first update our health factor to be a float to have the right type to do the comparison. Okay. Now that we did our check against our health factor and we verified that the account is under collateralized, we can process the liquidation. So the first step to the liquidation is going to be the liquidator has to pay back the borrowed amount to the bank. So we're going to transfer to the bank. So let transfer to bank equal, we'll do transfer checked. So this is what Copilot suggested. It's going to come from the borrowed token account. So we're going to update that suggestion. Now it's going to go to the borrowed bank token account. The authority is going to be the liquidator, and the mint is going to be the borrowed mint. Okay, so this is all for the borrowed token because we're repaying a borrowed asset. Now that we set that up, we can do the CPI program. Let's CPI program, and that's going to be the token program. And then now we can calculate the CPI context. And this is coming from an associated token account, so we don't need signing seeds. Then we'll specify the decimals, and these are the decimals for the borrowed mint. And then we can process the transfer. So we don't want to liquidate the total borrowed. Throughout this code base, we're actually using a close factor for the lending protocol, and the close factor is the percentage of collateral that can be liquidated. So we're going to update this by using the close factor for the liquidation. So we'll first calculate what the liquidation amount can be. And that is equal to the total borrowed multiplied by the liquidation close factor. So total borrowed and then we'll do liquidation close factor unwrap. Okay, now that we have the liquidation amount, we're going to paste that in. Now we'll just have to import our token interface. And that was our first transfer for the liquidation. Let's just update some of our types here. Okay, so for some reason, transfer checked was imported by token. So we always have to check our imports whenever we're doing an automated import through our VS Code. So we're going to get rid of that so we can fix our types. And transfer checked should go here. Okay, and we'll fix this import. So that got rid of our type error. So now we're going to process the second part of the liquidation, and that is transferring from the collateral account to the liquidator. It's going to pay back everything that the liquidator sent to repay the loan, and it's also going to include an additional amount for the liquidation bonus. So let's calculate what that amount is going to be. Okay, we'll name this liquidator amount. And this is going to be the liquidation amount that we calculated earlier times the liquidation bonus. So we'll go to the collateral bank.liquidation bonus. And then we're going to add the liquidation amount to that. So the liquidation bonus is a percentage. So we're going to take a percentage of the liquidation amount and add that to the original liquidation amount. Okay, now we can process this liquidation. So let's transfer to liquidator. That will be transfer checked. It's coming from the collateral bank token account. It's going to the liquidator's collateral token account. The authority is the collateral bank token account. And the mint is going to be the collateral mint. Now, because we're transferring from the bank token account, which is a PDA, we need to include the signer seeds. So we've written these seeds a few times. Let's just go back to where we have that and just copy it. Okay. Paste that in. Now we can execute the transfer. So we'll do let CPI context to liquidator equal, and this will be the CPI context of the CPI program. And then we're going to use the transfer to liquidator account. And then we're going to use with signer seeds. Okay. Next, we need the decimals. So we'll do let collateral decimals, and that'll be the collateral mint decimals. And then we can process this transfer. So token interface, transfer checked. Oh, and since we copied this in from our other function, the naming of these accounts are a little different. So this is going to be the collateral mint and the collateral bank token account. There we go. And that is everything we need for the liquidation. We need to also import this E. So liquidation is good to go. We'll go back to our librs and we're going to add our very last instruction for our lending protocol. And that will be liquidate. We'll pull in the context from our liquidate struct and process liquidate. And there is our last instruction for our anchor program. So now that we've finished all of our instructions, we just want to update our cargo toml with a few things, and then we're going to build our project. So we'll go to our terminal and we're going to cargo add, and we also want the Pyth SDK from Solana. Okay, and we're just going to change this to 10.1 for version compatibility. And then we also want to cargo add Solana program. But we're going to want version 18.17. So we'll do 1.18.17. Now, one last thing. Because we're using Anchor SPL, we want to update our IDL build to include Anchor SPL. So we'll do anchorling we'll do Anchor SPL / IDL build. There we go. If you do not update your IDL build to also include the Anchor SPL, your build won't actually build. So you need to include that section. Now, we'll be able to run Anchor build and see if our program compiles. And here you go. You can see everything finished and compiled. Now, up next is writing tests. All right, so for our tests, we're going to be using Bankrun. So we can navigate to our test folder. We can delete the test file that was automatically generated with Anchor in it, because we're not going to be using it. So move to trash. Now, with Bankrun, we're going to need to include a fixtures folder inside our tests. So we'll do fixtures. And we're going to copy our .so file that was generated when we ran Anchor build. So that was generated in our target folder. So we'll go to target, deploy, lending.so, and we're going to copy that. Now we'll go into our fixtures and paste it. Okay. Now we can create a file in our test folder for Bankrun. So we'll do bankrun.spec.ts. Okay. Now before we start writing out our tests, we want to update our npm packages. So we'll go to our package.json, see what we have. So far, our only dependency is Coral Anchor. So we're going to have to add a few things to be able to have all of the packages we need to run our tests in TypeScript. First, we're using Pyth throughout this project for our oracles. So we're going to need to use Pyth in our npm packages as well. So we'll do npm I at Pyth network dash, and it's the Pyth Solana receiver. Okay. Now that's added as a dependency, and this is version 0.8. We're going to do 0.8.0. Okay. So we're updating all of the versions where we know that they're all compatible for our dependencies. Up next, we're going to do SPL token. So npm I at Solana-SPL token. Okay. And then next is going to be Web3.js. So we'll do npm I at Solana-Web3.js. And then we'll need both Anchor Bankrun and Solana Bankrun. So npm I Anchor Bankrun. And I spelled that wrong. Okay. Bankrun. There we go. And then Solana Bankrun. And then because we're using SBL tokens, we'll need SBL token bank run. So here we're having a dependency conflict, so we're going to update our versions with our dependencies. So for Web3.js, we should have, let's do 1.94. Okay. Anchor bank run is 0.4. Solana bank run will do 0.2. Okay. Now we should be able to add in SPL token bank run. There we go. So for SBL token bank run, we're actually going to do 2.5. And then lastly is our RPC WebSockets. So now all our dependencies have been added to our project. We can go back to our bank run spec and start writing out our tests. So the first thing I want to do is get our IDL import done correctly, because this gets a little tricky sometimes, so we'll get that out of the way. So we want to import our IDL from the target file that was generated when we ran Anchor build. So we'll do import IDL from, and this should come from our target IDL dash, and let's see what it's named. So we'll go into our target folder, IDL, it's just lending.json. So we'll do lending.json. Okay, now we want the lending from our types. So we want the TypeScript compatible type file. So that will be in our lending TS, and this is type named lending. So we'll do import, and we want lending from target types lending. Okay. Oh. So now that import is all set for when we're going to need it when we declare our program in our environment setup. So first, we're going to set up our environment in Bankrun. So in Bankrun, it's generating a Banks client and a Banks server, and we want to make sure we have all of the correct programs and accounts that are needed and funded to be able to accurately test a full lending protocol simulation. So we'll do describe, and we'll do a lending smart contract test. Okay. And then async. Now we want to make sure we're using describe and it from node test for this to work properly. So we're going to update our import here to include describe it from not Mocha, but we're going to be using node test. Okay. Okay. Now that that's set up, we're going to want to start our Bankrun client, and we'll do that by running start anchor. So we'll do context is equal to await start anchor. And then we're going to import this from Bankrun. Okay. And now let's get our argument set up. But first, we want to define context. So let context. And then the type for context is going to be the program test context. So with Start Anchor, it starts a Bankrun in your Anchor workspace with all of the workspace programs deployed. So the first argument here is going to be your path. Since we created our lending.so in our fixtures, we can just make our path an empty string. Okay. And then next is going to be all of the programs that you want to deploy. So we want to deploy our lending program. So we need the name, which is lending. And you want to make sure that this name matches whatever your .so file is. If I named this lending project, then this would have to be lending project as well. Next, you need the program ID. So the program ID is going to come from your IDL. So we can do a new public key from IDL.address. And you're able to do that because if you go into your IDL, you see you have a key value pair of your address. Now we want to think about additional accounts that need to be passed through. So one account that we're using that we did not initialize within our lending protocol instructions is Pith. We're using the price update account from Pith. So we need to make sure that that account is also passed through. So this first section is for programs. The next section is for accounts, an array of objects indicating what data to write to the given address. So we're going to set this up for Pith. And what you need for an account is the address and the account info. So we'll set up address and account and info. But we don't have these fields yet, so how do we get them? So you can use the connection to be able to get the account info for a specific account address. So we need to get the Pith account from DevNet, and then we can use our DevNet connection to get the account info. So we'll first go to Solana FM to get the Pith account address. So if we go to Solana FM, we have the account for the Pith Solana receiver, which is this address. So we're going to copy this address and write that into our program. So we need a const for Pith, and that will be a new public key of this program ID. Okay, now that we have that, we're going to make a connection to DevNet to be able to query this account and get the account info. So we'll do const DevNet connection is equal to, we'll do a new connection of the Solana DevNet. There we go. And the connection is an import from Solana Web3.js. Now we can use a method on the connection to get the account info. So we'll do const account info is equal to await devnet connection dot get account info of the Pith address. So now we have the address, so we'll just pull that constant in here. And then we also have the info, so we'll pull that in as well. Account info. Okay, and we're missing brackets around here for formatting. Okay, so we have the name, lending, program ID, and we're pulling that from the IDL for the programs that we want to upload on our bank server. And then for the accounts, we have the Pith address and its corresponding account info. Now that we have that, we're going to set our provider for Bankrun. So we'll do provider is equal to new Bankrun provider. And that just takes in the context that we defined earlier. And then we're going to make sure we import our Bankrun provider. And then we're going to define our provider. So we'll do let provider equal a Bankrun provider. Okay, so now we have our provider. Now let's think everything else we need for our environment setup to be able to test out the lending protocol. We're going to need to be able to get the price feed ID and get the real-time price of a specific asset. So let's get that set up. So we can do const, and we need the sole price feed ID. And that is equal to, we already use this in our constants, so we can copy that over. Now we'll need the price feed account. So we can do const sol USD price feed account. Now we want to create a Pyth Solana receiver. So we're going to do that with the Pyth Solana receiver import from Pyth. So we'll do const our Pyth Solana receiver, and we're going to create a new Pyth Solana receiver. Now we'll import that from Pyth. And then you can see we have to pass through two arguments, the connection and the wallet. The rest are optional. There's one interesting thing about Bankrom where it doesn't have a connection natively. So we're going to use a Bankrun context wrapper that I pulled from GitHub, and we're just going to paste that in another file and be able to use some of the methods that are generated there. Let's go back a file and create a new folder for Bankrun utils. And inside that, we're going to do Bankrum connection.ts. And what I'm going to do is copy this entire file. The link to the GitHub repo that I pulled this from will be in the bootcamp repo for the lending protocol project. So we'll just copy this whole file. And this just allows for a lot of different functions to be used on the Bankrun connection. Now we'll go back to our Bankrun, and we'll be able to create a connection with Bankrun by using this new file that we just imported into our workspace. So we'll go back a few steps to add this in, and we'll do the Bankrun context wrapper. Is equal to a new Bankrun context wrapper of the context that we defined. Okay. And then we'll go up here. Bankrun context wrapper is a Bankrun context wrapper type. And you can see the import came from our Bankrun connection file that we just added. Okay. Now that we have that, we can generate a connection. So we'll do const connection is equal to the Bankrun context wrapper dot connection, and we're going to do to connection. Okay. Now that we have that connection, we can write our first parameter. So this is your connection. Okay. And then we just need the wallet, which is the provider dot wallet. And we're going to update that, and now we're good to go. So now we have the Pyth Solana receiver. Now we can use that to get the price feed account. So we're going to do const sol USD price feed account, and that will use the Pyth Solana receiver. Dot, and we'll get price feed account address. And then the first argument is the shard ID, which is 0. And then the second is going to be the price feed ID, which will use the sol price feed ID. Now that we have everything set up here, we have both the account address and the account info. Actually, we don't have the info yet, so let's get that. We need const. We'll need to generate a public key from this feed account. So we'll do sol USD price feed account. Just double check. Let's see. This is already a public key type, so we don't need to do that. Okay, so we'll just get the account info. So we'll do feed account info, and we'll do a wait. We'll use the devnet connection to get the account info of the address we just generated from devnet. So devnet connection dot get account info, And we're getting the account info from this Sol USD price feed account. Now we have both the address and the account info for another account that we're going to need deployed onto our bank run server and client. So we can update. Since we're doing this after start anchor, we can actually use set account to add new accounts. So we'll do context.setAccount, and we'll need both the address and the account info just like we needed earlier. So the address is going to be the Sol price feed account, and then the info is the feed account info. Okay, now all of our accounts are set up. So next we want to set up our program. So program is equal to new program of type lending. And then we'll do the IDO as lending. And then we need the provider. Okay. And then we're going to define our program here. And then we need to import program. There we go. Up next, we'll need two more things, the Banks client and the signer. We're just simplifying things because we're going to be using it a lot throughout the tests. So we're making their own variables. So Banks client is equal to the context.Banks client. And then the signer is equal to the provider.wallet.payer. Okay, and then we'll define those. And Banks client is going to be a Banks client type from Bankrum. And then signer is going to be a key pair because we're signing with it. So we need both the public and private key. And we'll import that. That should be an import from Web3.js. Okay. Oh, typo. There we go. Key pair, lowercase p. All right, so let's think about our environment so far. We have both our lending program deployed, we have the Pyth accounts deployed, we have the account for our Sol USDC price feed account. Now, we need a SPL token for both USDC and Sol. So as we mentioned earlier, typically lending protocols will use wrapped Sol here because it is an SPL token type instead of having to use the native system program and LAN ports to make token transfers. So we're going to generate two arbitrary SPL tokens for testing purposes and be able to use those as pretend USDC and Sol. So we'll do const mint USDC. And we're minting this to make sure that we have the correct authority needed to run our tests. So we'll create mint. Okay. And we'll import that. Wrong import. So where did it go? Create mint. Okay. We want to import the create mint from the SPL token background. So we're going to do import create mint from, and this is going to be SPL token bank run because we want this compatible with our bank run environment. Okay. Now let's look at, now for our create mint, the first parameter is going to be the Banks client. And then we'll need the signer. This isn't showing. Hold on. We need to wait for the IDE to load. So make sure we have the import in our package.json. SPL token bank run. Okay. Let's just double check everything. We'll run npm install. Make sure we have all of our packages. Okay. We'll go back here. Okay, may just take a little bit longer to load. But for our create mint, the first argument is going to be the bank's client. The next is going to be the payer, which is the signer. Then we need the mint authority. So the mint authority is going to be the signer's public key. And then we're going to need the freeze authority, which we'll set to null. And then lastly, the decimals, which we'll set to 2. Now we'll do the same thing, but for Sol. So we'll do const mint Sol, and we'll do await create mint. And this will have the same arguments. So we'll just paste that in. Okay, now that that's done, we're going to need a few PDAs. So we'll need both the USDC bank account, the Sol bank account, and the Sol token account. So let's start writing those. We have, first up is the USDC bank account. USDC bank account. And that is a public key dot find program address sync. And we'll do buffer from the treasury. And then for the bank's token account, it was the treasury and the mint address key. So we'll do the mint USDC to buffer. And then we need the program ID. So program dot program ID. Okay, and we should be using find program address sync because find program address is deprecated. We'll just fix some formatting here. This should be like that. Okay, and now we'll define the USDC bank account as a public key. There you go. And we're going to do the same thing for the Sol bank account. So this is pretty similar formatting, but we're going to update the mint to the Sol mint. So mint Sol. And then we'll define the type up here. Okay. And lastly, we need the Sol token account. So we'll do public key, find program address sync. We're going to do a buffer from, actually, that is the Sol token account. We did it already. We're just naming it correctly, Sol token account. There we go. So this is our environment setup. Now we can start with our first test. So we're going to do it. We'll test initializing both the bank and funding the bank. So we'll do test init and fund bank. Async. So let's define our transaction to init the bank. So we'll do const init, and we'll start with the USDC bank. We'll do await program dot methods dot init bank. And then when we initialize the bank, it takes in the liquidation threshold and the max LTV. So we'll do a new BN, we'll set it to 1, and we'll set the other to 1 as well. We need to import BN from Anchor. Now we need the accounts. So the accounts here are going to be the signer, which is the signer.public key. And then we'll need the mint. And since this is the mint bank, we're going to do the mint USDC. And then we'll need the token program. So token program is equal to, and we'll do the token program ID, import from Solana SPL tokens. And lastly, we are going to set our RPC with commitment confirmed. Okay, now let's console log this transaction. So we'll do console.log, and we'll do create USDC bank account. And we'll just log the transaction. Okay. Now that we've created it, and we have the mint authority on the USDC token that we created, we're going to mint tokens into this account. So let's define the amount that we want to mint. Const amount. And then we'll define the mint transaction. And we'll use mint2, which is also going to be coming from the SPL token bank run. So we'll update our import here. And then for mint2, we're going to pass through the client first, and then the signer. And then we need the mint address, so we'll do the USDC mint address. So that is, oops. And now we'll need the destination, which is the USDC bank account. And then we'll need the signer and the amount. Okay, and then we're going to console log that. The next test to write is going to be initializing a user. So let's do it test init user. Okay, so now we'll define the transaction there. Init user tx is equal to await. We'll do program.methods.init user. And here we're going to pass through the USDC mint account because that is the argument that it takes in. And then we'll need the accounts. And that will just be the signer. Okay. Now we need the RPC. And now we'll console log that transaction. So we've initialized the user, we've initialized the USDC bank. Now we want to initialize and fund the Sol bank as well. So let's do it test init and fund Sol bank. Okay, so we'll do the init Sol bank transaction. We want to init the bank. We'll set the liquidation threshold and max LTV. We'll set the accounts, which will be the signer. The mint is the Sol mint, and then the token program is the token program ID. Then we'll set the RPC. There we go. And now we'll want to console log that. And then we want to fund as well. So we'll set the amount. And then we'll do the mint transaction. And then we'll console log our mint transaction. Okay, great. So now we want to create and fund token accounts for the user. So the user has token accounts to be able to execute deposit, withdraw, borrow, repay, everything they need to do. So we're going to create and fund token accounts. Okay, so first let's make the USDC account. So USDC token account. We'll do await create account. And this is also going to be an import from the SPL token from Bankrum. So we'll update this to have create account. Okay. And now to the create account, we're going to need the Banks client, the signer, the mint for the USDC, and then we need the signer public key. Okay. Now that we have the token account, let's console log that. And then we want to fund. So we're going to const amount, and then const, and we're going to mint USDC TX, and we'll do await, the same thing we did earlier, mint 2, and we're going to do the Banks client, signer, the USDC mint, the USDC token account, signer, and amount. Okay. There we go. Clean up some formatting, and now we'll just console log that. Okay. So now everything's set up for us to actually test our 4 instructions. So let's first test our deposit. So we'll do it test deposit. So let's define the transaction. And we're going to deposit USDC since that was the token account that we funded, so we have those funds to deposit. And we'll await program.methods.deposit. And now we'll define the amount that we want to deposit. So we'll do new BN, and we'll just do a large amount. Now we need the accounts. We have the signer, we have the mint, and we also have the token program. Okay. Now we'll need the RPC, commitment confirmed. And then we're going to just console log that transaction. So we did deposit, now we have collateral in the protocol. So now we want to borrow against the collateral that we have. So we're going to borrow, we'll do const, well, we'll define our test first. It's test borrow, okay. Now we'll define the transaction. So we're going to borrow SOL since we deposited USDC as our collateral. So borrow SOL, program.methods, borrow. Now we want to take into consideration the liquidation threshold. So we're going to borrow not as much as we deposited, and also SOL is worth more than USDC. So just to be safe, I'm going to just borrow 1 SOL. We'll do new BN of 1. Okay, now we need the accounts. We'll have the signer. We'll have the mint, and this will be the SOL mint. We'll have the token program. And now we also need the price update account because the borrow function is using the Pyth oracles. And we're going to use the SOL USD price feed account. We'll clean up some typos. Okay, there we go. And now we'll just need the RPC. and then we'll console log this transaction. Okay, so now we have deposited, we have borrowed. Now we want to be able to repay the loan that we borrowed. So let's test our repay. We'll define the test. And we're going to define the transaction, which will be repay SOL, because SOL is the asset that we borrowed, so we want to repay the same asset. And we're going to repay, and we're going to repay 1. Okay. Now the accounts that are needed here, we'll do the signer, the mint, and the token program, and then RPC, commitment confirmed, and then we're going to console log this transaction. Okay. So we've deposited, we've borrowed against that collateral, we've repaid the loan that we borrowed. Now all we want to do is withdraw any extra collateral that we have deposited on the protocol. So the next function we're going to test is withdraw. Okay. So we're going to withdraw USDC. Let's just withdraw 100 and leave some in the protocol. Okay. So the signer is the public key, the mint is the USDC mint because that is the collateral that we deposited into the protocol. And then we have the RPC and we're console logging that transaction. Okay, so now that we have finished our test, we're just going to run anchor test and make sure everything worked. So we'll do anchor test. And then it's going to compile everything. Run the test suite, and you can see all 8 tests have passed, the suite has passed, and if you want to look at all of your console logs, you can scroll through all of the bank run output in your terminal. And now you're good to go. So we have created a lending protocol that allows a user to deposit into a bank and earn interest, withdraw the amounts that they have deposited, or borrow against the collateral that they've deposited, and also be able to repay their loan. We've also enabled liquidators to be able to come in and liquidate unhealthy accounts, and we tested everything using Bankrun. All good.